Now members, we are going to see some good example in polynomials. It's about this proof, but please don't forget to subscribe to the channel. Now this one says, given that f of x is this, where q of x is a remainder, I mean is a quotient, g of x is that, of course it's the divisor, and r of x is the remainder. Show that r of x is equal to this. Now, if or is that if this is the quotient, it means that this one is going to be the divisor, using the formula we used of the polynomial is equal to the divisor times the quotient plus the remainder. Now, because our quotient, I mean our divisor is quadratic, or is a remainder is a powerless. So if the divisor is quadratic, it means that the remainder is going to be linear. Now, that's why I'm saying that r of x be ax plus b. So this expression is linear. Why? Because of this divisor, so when I expand this, I'm going to be having a polynomial to degree 2, which will be quadratic. It means that now, the remainder I will get, it has to be in a linear form. So that's why I'm saying r of x be ax plus b. I explained this, all this, in the remainder theorem. Hope you remember, recall that lesson. So now, they told us that r q of x is given by this from here. Then q was a quotient, then plus. Now our remainder, we have said, let it be a linear function like that for the reasons now we know. Because if this one is quadratic, the remainder is linear. Okay, if the polynomial is degree 3. Now, they are telling us that now, what do we need? We need now to get the remainder. They are telling us that the remainder should be given by this. So we need to eliminate A, and we also need to eliminate B. But now, here I have these two factors. Now I'm saying, if my x is equal to alpha, what I'll be adding now, f of alpha equal to, when I put here alpha, this will be alpha minus alpha, which will be 0. The whole of this now will be 0. So here I'll be adding A, alpha, then plus b, as simple as that. I call this equation 1. Then I say, if my x is equal to, now see I have negative beta, is equal now to beta. I'll be adding now, we put here where there's x we put, so you see I have f of beta will be equal to, when I put here beta, to be 0, the whole of this will be 0, so here I'll be having a beta plus b. I call this equation 2. Now it's that I need to eliminate to get the value of a and to get the value of b. Because in my proof you don't say anything like a and b. So it's that I have this and I have that one. So that we can eliminate b. Because it has coefficient 1 here and here coefficient 1. What are we going to say? We are going to say equation 1 minus equation 2. So it's that now I have f of alpha equal to a alpha plus b. Then this one I have f of beta equal to f beta plus b. Then the same, I'm going to subtract. I subtract this, I get f of alpha, f of beta equal to this minus this, which I'll be having is that a is common, so I'm going to factorize out a. Then alpha minus beta, alpha minus beta, b minus b, it will go to 0. So you make any subject. If I make any subject, from here it's that 9f, f of beta, over, divided by this, alpha minus beta is equal to a. So this is the value of a. Now, still I need to eliminate now a so that I can get b. What am I going to do? What I'm going to do, I'm going to multiply. So I need to eliminate a. So the coefficient here of a is alpha, here it's b. So I'm going to get beta, we multiply it in this equation. Then we get alpha, we multiply it in this equation. So we are going to say alpha in equation 2, then minus, then beta in equation 1. So that's what they are going to do. So now from here, it's now in equation 2, this was R1, remember this is R1, this is R2. So in 2 we are multiplying alpha. We are multiplying here alpha, I get alpha f of beta equaling to, here we are having a alpha beta, then plus alpha b. Then in equation minus, we are now multiplying in equation 1, we are multiplying beta. So now multiplying here beta, I have b f of alpha equaling to, multiply here beta, I get a alpha beta, then plus here we are having b, okay, beta, we are having beta, b. Then we subtract these two because we want to eliminate this and they are having the same signs. So that when I subtract this, I get alpha f of b minus beta f of alpha equaling to this minus this, it goes. So it's that here our b is common, so I get alpha minus beta into a b. So make b the subject, is that now my alpha f of beta minus beta f of alpha divided through by this alpha minus beta equaling to a b. Now I have a, I have b. But I know that now my r of x, the remainder was given by ax plus b. Now I have a, I have b. Can we substitute? So my a, I substitute a. My a is this, so f of x, f of alpha minus f of beta, the whole over alpha minus beta. But remember, the whole of this I'm multiplying through with x. Then plus our b from here is here, alpha minus beta of alpha, then over alpha minus beta. Now from there, so that the same LCM means that we shall add. This time this I get x, f of alpha, this time this, f of beta, then plus alpha, f of beta, minus beta, f of alpha, the whole, now the same LCM, alpha minus beta. So now it's that we put things cross. So that this one according to our proof is that we have x minus beta. So you put this one, f of this one is common with this, so this will be now x f of alpha minus beta f of alpha. Now plus, so I have this alpha f of beta minus x f of beta. The whole thing over alpha minus beta. So it's that my r of x is going to be, what is common here is this. So when you factorize r f of alpha, here we have x minus beta into f of alpha. Here what is common? F of beta. So you factorize f of beta, here we have alpha, here we have x into f of beta, the whole over alpha minus beta, and that is our proof, as you can see in this question. So that's it, members. I will see you when.